Redshift is represented by the letter Z and can be quantified by wavelength, frequency, or energy. More redshift is a higher Z and a longer wavelength, with a reduction in frequency and energy. When Z is negative, that's Blueshift, where all positive values of Z are redshift. Inverting the equations quantifies Blueshift, represented by the letter B. A higher B is a shorter wavelength, but with more frequency and energy. When B is negative, that's redshift. The range of redshifts is infinite as Z, but finite as negative B. This can be very useful. The redshift distance relationship for small z's is d equals z times Hubble's length. That's what c over h sub 0 is. Substituting negative b for the z, we get a new relationship. Since 1 plus b equals 1 over 1 plus z, a little bit of algebra simplifies to b equals negative z over 1 plus z. Therefore, our new equation is d equals z over 1 plus z times Hubble's length. Compared, the two distances are different. The redshift distance relationship climbs to infinity, while the Blueshift distance relationship converges on Hubble's length. Compared to the concordance model of cosmology, lambda CDM, they're actually very similar. And when you adjust the parameters to remove dark energy and the effects of gravity on redshifts, they're actually a perfect match. Mathematically, this is known as an empty FLRW model. In summary, Z is proportional to wavelength, while B is proportional to frequency and energy. The range of redshifts is infinite as Z and finite as negative B. The distance law for Z's only works for very small values, while for B, it is approximate to lambda CDM and equal to an empty FLRW model. In a follow-up video, we'll see how the equation compares to observational data. Thanks for listening. Please leave a comment.